Recently, I got called up to Boston to do a one-day training with a builder who's having problems with humidity. And it's the kind of thing where they'll say, oh, we're getting these callbacks for humidity, and they kind of at first don't believe it, and their mechanical engineers don't believe it. And so they're not having any dehumidifiers specified for their apartments that they're working on, these condos that they're only in charge of one unit in an entire building. It's just a build out where they gut the thing, rebuild it the way that the client wants. I ran them through this simulation. The problem that I came up with is that when we did the calculation, and I'm using these anecdotal numbers from Building Science Corporation, on a hot day, we're going to have a stack effect, which is warm air rises, cool air sinks, of 1.5 pascals per floor. Air sinks through the building. You can see here, we end up with a pressure of, in a 71-story building, which they are building one of in San Francisco, and it's an affordable housing. Partially, it's a mixed income building. So this may be your family or your friends who end up in a place like this eventually. You'll end up with plus 53 pascals in the bottom and negative 53 pascals. That means that a blower door test is basically running at the bottom floor and the top floor of this building. That's kind of a special height. On the flip side, in the wintertime, we end up with a total pascals, 4 pascals per floor times 71, of 284 pascals top to bottom. And of course, because of this neutral pressure plane that I pointed out first, this dotted line, we end up with plus 142 at the top, minus 142 pascals at the bottom. What that led me to is to do the infiltration calculation. They're getting like 635 CFM of infiltration in this penthouse. And that leads to about 400 pints per day dehumidification needed. And the mechanical engineers were speccing, you can guess, 0. I know that it can't be either one of those. It's got to be something in the middle, but like, how do we do this? And so I know also that there are people living in penthouses with no dehumidification built in.
Let's start with the negative pressure to begin with there, the negative stack effect in the summertime. But before we do that, where is the building? Is it in Boston or is it in Miami?
Are we talking about humidity ratio to actually get the actual humidity coming in?
Talking about the number of hours at risk.
Oh, okay, cool. Let's put it in Boston, since that's near where you are, and that's where I was when I was presenting on this and came up with this conundrum.
Okay, great. So 70-story building in Boston, and it's built tight. Where I would have a different perspective on the pressure difference is whether or not each of these floors has been truly isolated from all the others. Now, if you have an open stack, what you end up with there at 90 pascals is very reasonable. And I'll give you an example of one that we worked on a number of years ago in St. Louis, the Eagleton Courthouse, which was built by a contractor that was not the best contractor and built a design that was not the best design. So it was basically an open stack, and they ended up with a lot of air infiltration. And we measured the pressure difference at what amounts to the penthouse. It was not 70 stories, but it was maybe 30, something like that, something 35, something in that range. And it was 70 pascals. But that's because there was no floor-to-floor separation effectively, which was a real problem in two respects. One is obviously it's a huge pressure difference to try and maintain. And the other problem is fire. So basically what you've done is you created a chimney so that any fire anywhere is going to go up, and it's going to go up really, really quickly, or down depending on the season. So it's a catastrophe, and they don't usually build them that way. So if you were to take a measurement in Boston at the top of a 70-story building and measure the pressure difference between the penthouse and the outdoors, you're not going to get 70 pascals or 90 pascals, because it's going to be built tighter these days than it would have been back in the day.
So where we would first want to start is to figure out the maximum possible stack that can be acting on this building. So, we look at the number of stories in a building, we make an estimate on the floor to ceiling height in that building. And then using a stack calculation, we can figure out, okay, so what is the maximum stack pressure that we're going to see at the top of that building? Now, the maximum possible stack is not what we're actually going to see in a real building because we've got floors that separate that vertical column of air. That separation acts to reduce stack effect. And so we need to take that into account.
So that's kind of like when we're doing a blower door test on a home and we do zonal pressure testing and we kind of close that door to see what happens behind it. That's what the floors are essentially doing, is creating a different zone. So ideally, if the pressure per floor when it's all one giant chimney is one thing, when you put those floors in there, it's diminishing it so that it would be like substantially less potentially.
Absolutely, yeah. Now, in real buildings, it's complicated because you've got these floors which provide this really good separation, but you've also got elevator shafts and stairwells and all of these vertical chases that do connect the floors. So we use what's called a draft coefficient to modify the maximum stack pressure. So that can be in a real building anywhere between 0.3 and 0.6, and it varies, but just to give you a sense of what that is. So think about that. We're reducing that from 30 to 60% of what the maximum stack pressure would be. So that already brings your number fairly significantly down.
And then just to clarify, that is in older buildings without air tightened elevator lobbies, and in newer buildings that are like the ones that are following your recommendations that are actually being built to try and contain that, to encapsulate each floor?
Yeah, so the tighter buildings are going to be at the lower end of that. So and even below that 0.3. And then, yes, the older buildings are going to be sort of more 0.6, maybe 0.7, somewhere in there. So vary quite a bit because there's a lot of variation in real buildings, as we all know. So.
And then one last point, in this penthouse scenario, if there is a wealth hoarder at the top of this building that has an elevator that opens up directly into their apartment, that's actually worst case scenario, right?
Yeah, because then you're directly connected to that volume of air, that vertical volume of air that extends all the way through the building. So that's probably not a great scenario.
Great. Okay, so we take the 4 pascals per story in the wintertime, or the 1.5 pascals per story in the summertime, these kind of anecdotal numbers that come from Building Science Corporation, and we're reducing them to what in your model?
Yeah, I had about 0.6 pascals per floor under the summer condition. Actual estimates are 0.35, after I added that draft coefficient. 25 Pascal difference from the neutral pressure plane to the top of the building, and then again from the bottom of the building. So you're going from 0 to 25.
Got it. So whole building is 50 pascals blower door test, but we got minus 25 at the top floor, plus 25 at the bottom floor. So half a blower door test. Okay. Okay, great. So that makes a lot more sense. That's still a considerable amount of air leakage, though, like going under half a blower door test just all day long on a 90-degree day.
Yeah, it's so completely typical for design engineers to say there isn't any humidity load. We don't have to worry about it because they don't think about it a lot until they run into trouble. And if you're in Boston and you're talking to local design engineers in Boston, they would be, depending on who you spoke to, either very aware that this is likely to be an issue or completely oblivious to the idea that there would be any issue with humidity. Because in most buildings in the Boston area, there aren't enough hours of problematic humidity to really focus your mind on that subject. You're more concerned with other things. And
can we talk about time scales for a second? When you say there's not enough hours, do you mean enough hours in one day? Meaning there's
1 year. 1 year.
So even if we have an entire 2-week span of humidity buildup, you're saying the next 2 weeks after that will bring it down? Is that kind of, you're thinking of terms of, I mean, a year seems like a lot of time. Mold can build up fairly quickly when it really wants to.
And it does. It's a combination of both things, really. I think, Corby. If you've got the annual issue, so now you got drying of the structure and stuff that happens in the wintertime. Actually, in the north here, we saturate our structures in the wintertime. We have very high relative humidity, so we saturate our exterior walls in the winter. Never mind that. The point is you have a good wetting and drying.
What numbers did you come up with on the wintertime?
Guesstimating from the delta T, it's probably going to be about double to triple depending on the winter day that you're looking at.
Maybe triple a blower door test, which means 75 pascals minus at the bottom, 75 pascals plus at the top. And even a blower door test of 50 won't turn that around. So in the wintertime, we still couldn't reverse the pressurization that's happening in that penthouse apartment to get air from outside to come in so that we could feel the drafts and see it with infrared. It would always be pressurized unless you could find a big enough fan to really turn around 75 pascals of pressure, right?
Yeah, you might need like a double fan or triple fan. Well,
Which
maybe
you have. You've got 6, right? Or 8?
well, 7 or 8, I think. Yeah.
Yeah. Okay.
And to your point, you might have a week of really nasty weather, but you're not going to have a month of nasty weather. And you may well have diurnal changes too that will help you out. And that's also true where you are in Atlanta. You're going to have the same kind of thing. You've got many more hours of high humidity in Atlanta than we have up here in Boston, but you do have a day-night thing for many of the seasonal things. So
here's a question that you actually helped me understand in the beginning when I first started, owning you as a mentor.
it's yours, take it. I don't want it anymore.
When the temperature goes up in the daytime and then down at night, you pointed out that the relative humidity on the scale will go down. So in the daytime, it's down, and then at night, the relative humidity. Does that not mean that the actual moisture content in the air, whether the temperature is high or low, day to night, is basically the same? So wouldn't it be kind of a concern overnight for this kind of a calculation?
Long subject, long conversation, but and you're thinking about it certainly the right way. You have higher relative humidity at night than you do during the day, during the swing seasons, but the other thing that you do want to think about is the fact that was not apparent to me until I started looking into it about, I don't know, 25, 30 years ago. 25 years ago. So for about the first, 20 years of my career, I'm thinking it doesn't work like this. And then I realize it does. And the way it works is that, let's say during the summertime or during the spring or during the fall, you can really track the outdoor dew point along with the outdoor dry bulb. So if you have let's say you have dew at night, and then in the morning, so it's 100% relative humidity or something close to it, certainly on the leaves of grass. And then you have a rising temperature during the morning, and all that moisture evaporates off. And you can track it as there is more energy in the system, there's more heat, and therefore there's more evaporation, and therefore until you run out of wet surfaces, you have a continuing rise, and that doesn't stop until the late afternoon in a lot of areas. It's temperature is going to go up. The dew point temperature, the humidity ratio, the grains per pound is going to go up along with it, and then come back down.
Very interesting.
Yeah. The problem is in all residential occupancies now is that we are ventilating them. So your 70-story building in Boston is not going to not have ventilation for each apartment. It's in each condo. It's going to have ventilation. And that's where the design engineers simply have not been thinking about this in a productive way. And that's how they get into trouble. And candidly, that's how we've seen problems in passive house. Same idea. We have almost no load, almost no cooling load, almost no heating load, and we don't have equipment that circulates a lot of air in that situation. It's tough to buy equipment that doesn't exist. And therefore, you end up with mold problems because of continuous ventilation and no dehumidification in what is otherwise a superb building. We have to take the water vapor out of the air if we have ventilation.
And so when we're under this condition, what is your feeling about the amount of ventilation that we should have to worry about? Is that negative 25 pascals in the summertime actually just enough to drive all the infiltration that we need? Do we actually need to follow any active mechanical ventilation?
Let me see. You're looking at about almost 100 liters per second of air. So that's quite a bit. You're not really going to need anything else. So yeah, no, I'd say the infiltration is going to be more than enough to address those needs in that apartment building.
I have to do a conversion now. 100 liters per second. 93 times 2.118 is 196 CFM.
Tons.
Continuous. Okay, cool. And that's going to be coming through the filter of the building.
Oh, yeah.
Okay. But then in the wintertime, would you say, first of all, we do need mechanical ventilation from outside because all the air is coming from the units below. But can we even like most of the systems that we're looking at are designed to put up with like up to an inch of water column resistance. So since we're not near that, we could actually still try to push air from outside into the unit, even though there's also air coming up from underneath trying to push into the unit, right?
Yeah, this is where it starts to get tricky. And where tracer gas testing and things become really helpful to see where that ventilation air can actually go. Because I think it depends a lot on the type of ventilation system you're using. So it is an in-suite system. Is it some sort of central system? Is it, I really hope it's not a pressurized corridor system. Like there's a lot of different ventilation approaches that would yield different effectiveness in terms of getting that air to the suite.
In Boston, during, late July, early August, maybe all the way up into September in some years, it's going to be like humidity that you have in Atlanta. It's still not going to be like humidity you have in Tampa, Florida.
Mm-hmm.
It's not going to be like humidity that you have in Phoenix in September, where it's monsoon season. Yeah.
So would you say that there's some reasonable amount, if we're saying like 400 pints per day for a 2,000 square foot condo, which sounds like, can we really do that? Would anybody actually do that? And somewhere between that and zero, what do you think would be a reasonable, if this was your family that was moving into this place, what would you tell them?
So we're talking about the penthouse at the top.
Yes.
And it's a modest 4,000 square foot or something like that for a penthouse.
Let's say 2,000. Yeah, let's say 2,000.
Okay, so there are four penthouses up there, and they're 2,000 apiece. Okay, all right. Yeah, so it isn't going to be 50 pounds. It's not, because you really don't have the infiltration. You just don't. You do have infiltration, but a modern building built to modern standards, and especially one built in the Boston area with Massachusetts codes for air tightness and commissioning, you're not going to have that much infiltration. You will have ventilation. 50 pints is going to be fine. 50 pint dehumidifier is going to be fine. No dehumidifier, big problem.
I think the big leap is getting from pressure to flow. And that's where I was really uncertain, just kind of pulling numbers out of thin air. So I went to the LEED ETS, the environmental tobacco smoke air tightness requirement. And I used that as the assumed leakage area, but just on 3 sides. So you're in a penthouse, so 2 sides exposed, 1 on the roof. That's where the infiltration is coming from. So if you're wondering where those numbers came from, and I can send you another photo of this if you need the.
Please, because actually that ETS standard, for everybody who doesn't know, is environmental tobacco smoke. That rule that's in that LEED high-rise standard is where I first was like, this can't possibly work on to like a team of mechanical engineers. They wanted to have, I believe the standard is they want to have 5 pascals pressurization of the corridor with respect to the unit on every floor. Isn't that what the standard says?
Appropriate to prevent contaminant concentration, or sorry, to prevent contaminant
transmission between units.
Yes, sorry.
But what we just went over is that every single floor's corridor and units have a different relationship to each other. So that would really take somebody of your caliber tuning every single floor's ventilation system, not just in the design, but also in real life, going out and testing it and tuning it.
One kind of interesting idea that we use in commercial buildings, but we don't use in residential buildings, probably because of the first cost, is variable air volume boxes that can dynamically respond to pressure changes. I feel like that's really the way to combat this. Like you need the combination of really good compartmentalization, but then you need some way of controlling airflow, because the building's only balanced the moment it's balanced. As soon as the temperature changes, it's not balanced anymore. So I think we need to stop talking about balancing in that way.
One last thing I want to ask you about. I have said, and I would love to be corrected by you, I have said that a dehumidifier, residential dehumidifier, can't take all the humidity you want to strip out of it in one pass. It needs multiple bites at the apple. And I started saying that because people were saying, oh, makeup air comes in hot and moist from outside. Why don't we just put a dehumidifier in line? And I was like, great, I'll show you what an 800 CFM dehumidifier looks like. And it's like, as big as a fridge. So I want to be correct about what I'm saying. When people are running a ventilating dehumidifier and they're bringing in 90-degree air that's raining outside, for example, some horrible, hypothetical, am I right that that dehumidifier can't possibly strip all that humidity out of it, that we need to keep it running? So if we're running it, 24 hours a day, bringing in 75 CFM through that outdoor intake, are we potentially creating a problem where we might be actually upping the humidity the same way that an AERV or even worse, an HRV would?
I think it really depends on the configuration of the ventilating dehumidifier. And how it is controlled. I will say that my thinking on this has morphed over the years, and what you're describing there as, the way to do it, which is absolutely the way to do it for a commercial building, which is a dehumidifier on the ventilation / makeup air. There's no question that's what it ought to be. Not that people always do it that way, but that's the way it ought to be. For residential, my thinking has evolved on that. I'm thinking that we don't need to do it that way, partly for the reason that you're describing, also for the reason that if you can get some recirculation, that's probably going to be a good thing. Partly for the reason that you mentioned in terms of capacity over time, and also just the ability to shut the ventilation off if you're going to be gone, and still have dehumidification that's occurring in the space. So I think ideally a blend of ventilation air going directly to the dehumidifier is a good idea, and then you bring some return air back to that same location before you go through the dehumidifier, so that you have a recirculating loop as well. I think that's a really ideal way to do it.
Last question. Do you think that the mechanical engineers who are out there working, designing these buildings right now, do they know the things that you know?
I'll say I think they're learning. We're seeing, at least locally, buildings that experience pretty severe effects of stack. Elevator doors won't open or won't close. You see real operational challenges when these huge pressures build up in these buildings. So I think as an industry, we're starting to learn about those challenges in tall buildings, but I think we have a little ways to go, especially when we think about distribution of ventilation air in buildings.
So I hope you have found this interesting. This is a conversation. There are questions to ask. Ask the right questions. Have these discussions with your engineers, with your builders. Make sure that if you're going to look at a high rise, take a manometer with you. There are people that you know who have pressure gauges, whether it's your HVAC contractor cousin, or you could now buy your own pressure gauge for $400 or $600. Like, normal people can get this stuff. And finding out what the pressure actually is on the day that you go to the open house at this high-rise condo, either on the bottom floor or at the top floor, might be very useful to you. And you can see a playlist where I test hotel rooms as an example of how you could kind of start to use just a little bag full of instruments that are like not that expensive these days. You would be amazed at what things used to cost, to start to investigate the invisible dynamics around us. So please do comment below if you have other things to add, or if you found stuff that we missed in this video. Like and subscribe. Tune in next time.